Hello everyone. Thank you for having me in this conference. It's really a big pleasure for me to be here and to present my topic, which I would say is booming last years, and especially when pandemic situation struck. I would say that digitalization topics are on the fire, and water management is not exception as well. So let me introduce my topic, which is about sustainable firefighting analysis and using hydraulic models of urban water supply systems. And I will shortly present you a real case study from Lithuania, from Alytus city. And my name is Paulius Grigaliunas, and I work in Sweco, Lithuania as a project manager. And last years, I work a lot with digital models of water management systems. And here on the right side, you see the general topics of today's presentation. I will briefly present you what is up to date, or let's say modern hydraulic model, and how it is integrated into digital or digital twin framework or models. I will also briefly present you what are the major steps when you build a model, and what are the digital integrations between GIS systems and other systems which uses water utility companies. The next big portion will be case study from Alytus city. I will briefly explain you how the model works, what can be checked in case of fires. And I will also conclude and give you some summaries or future insights for the future, how the models could be used and how they could be make even better. Okay, so what is the hydraulic model of water network? In very general perspective, hydraulic model is a big piece of cake and city's digital twin model. I am absolutely sure that most of you know what is hydraulic model, but in case of having some different understandings, I would briefly present you what is the modern digital model. And this topic is constantly changing and evaluating. The general purpose of this slide is to make sure that we talk about the same and from the same perspective. And as you probably noticed, the background picture presents the constantly changing environment where everyone is so busy in growing cities, especially in big mega cities. So water management networks are growing as well. And the general question is, do they grow sustainably? Do we really cope with all upcoming problems like water scarcity, climate change, and frequent fires, as well as extreme temperatures and so on? Those factors affect water management system at a very high level, and I would say in Lithuania last years were totally crazy, because temperatures, air temperatures during the summer are growing, and water demands are growing as well. So systems have to cope with that. And in case of emergency or in case of fire, you need to check if you have enough water to cope with your fires and to work with that. So digitalization comes into action to solve many problems in this case. And hydraulic model is a piece of cake in this big picture. And here on the right side of the screen, you see some abbreviations of digital models, what they have to represent and what general tasks are assigned to them. For example, digital models have to represent the assets in the physical world with a digital model. And the models are not just the models, they have to include relation interactions. They have to look and feel like real environment. They have to simulate models forward with varying degrees of precision. They have to be autonomous, and also in the near future, they will make some decisions. I talk about artificial intelligence integrations and so on. And it also have to connect with relevant time data to ensure the model mirrors reality in real time. Okay, so what are the major tasks for hydraulic modeling? So these are the very major and very general tasks like sustainable maintenance of water network system, water network optimization and network performance questions and tasks, how to reduce power consumption, how to reduce water loss and water scarcity, how to control water age and quality. Water age means the time from the time when water is extracted from the wells until the final client. Also, it also helps in planning and sustainable development of water supply networks and optimal use of existing network resources. And the last, but not least, fires. How to analyze fires, how to calculate fire water flows, and so on. And today I will talk about that. And in very general, it has to simulate situation and give you the answers. What if something goes wrong? For example, you have some power losses in wells, in pumping stations. You have to close some parts of your network system, and so on. And those are the major steps which you have to do when you create a digital model of your water system. There are some big groups, or let's say steps, which you have to do before you create really good and real-time based hydraulic model. So at first you have to have sustainable asset management and digital attribute system. You have to also work with your GIS system and topology plans. And only then you can create your digital model. And after that, of course, you can make your model, let's say, more live. You can integrate it with GIS, SCADA, or asset management systems. You can integrate it with BIM, building information models. Then you can have a real digital water model. Then you see all the pipes as a real structures. And the last box, let's say, it's a digital control room where you can control your management system, your water management system, let's say from home, for example. Okay, and here we have sustainable architecture, the layout of sustainable architecture of hydraulic model system. And scheme shows major integration blocks with existing city or water utility company data. And I will quickly represent you those integrations and their advantages, especially for firefighting. So the big block is direct custom meter integration. If you want to have real-time data, if you want to check the real situation in your system, you have to also have real-time data from your customers. Then the next block is GIS, the database integration. If something is changed in the system, you can quickly update your digital model with your GIS system. And also very important question when you talk about firefighting, real-time SCADA data integration. When you have a big fire, you can see the real situation in your model, and also it represents the real-time situation in your water network. Then you can make changes very fast, and you can see how those changes or water demand affects your real-time model and also real situation. And those are very general breakthroughs or general ideas why you need to have real or let's say digital models of water management systems. And the good practice in water management and fire safety system design is that at first you create a hydraulic model, you test it, you test everything, you find perfect solutions, and only then design and build. And the best option is that you test your hydraulic model and water management system in the master planning stages. Water management and fire safety standards and rules, also instructions for fire hydrants, flows, pressures, management, safety, and so on. Are they really comply with the rules, and system designers or maintenance engineers without models? This is the question. Then you design systems, but how do you know that you have enough water, enough pressure in any point of your real water management system? You can check that with a model at first and then design your system. The next question is, how do we plan water and fire water future developments? How do we know that our system works efficiently and sustainably? And in case you are a plot owner and you want to use existing water pipes for fire water systems, and water utility company gives you only the half of your demand, what to do, and maybe there is an option to receive or to get the full capacity or full water demand. But that must be checked in a hydraulic model first. And in case of fire, how do we test, check, control, and monitor water demands and whole system status? And the last one, how do we design water management systems which complies with fire safety standards and green ideas? And now, since we have some information, what is a hydraulic model and what are the major components of hydraulic model, let's move on to the real case study in Alytus city. So we have 4 different scenarios on the left side of the screen. You see what are the fire flows, what is the duration of the fires, and on the right side of the screen you see very rough and very quickly represented system layout in Alytus city. Here we have 2 different pressure zones, high pressure zone and low pressure zone, and you see 2 fires, fire number 1 and fire number 2. Here you also see that system has some reservoirs and pumping stations. And now let's jump to the fire scenario number 1, G1. So first fire, or fire number 1, the demand of water is 25 liters per second, and fire number 2 is 2 hydrants under 25 liters per second. So in total we have 50 liters per second. And it's very important to say that we test the fire during the time from 8 to 9 p.m. when the water demand from the whole city is higher. So total fire duration is 3 hours. And I will quickly just give you few sentences about results. In this case, water management system status is okay, and only some moderate fire flow pressures in higher altitude areas is about 1.6 bars, and that is okay, I would say. Okay, let's jump to the fire scenario number 2. Now we have fire number 1, 25 liters per second, fire number 2, 5 hydrants under 25 liters per second. So in total, we have 100 liters per second in fire number 2. Time duration is the same, from 6 to 9 p.m. And here we have some different results. I would say that water management system status in general is okay. But we have some lower pressure zones, like 1.5 bars in higher altitude areas. But in total, I would say that this fire is not so big, and the water management system can cope and can work with that. Okay, fire number 3. The general idea to check this scenario was to check what is the maximum available water flow in selected fire locations. So we have 2 fires, and we want to know what is the maximum fire water flow is available in the system. And we also want to check minimum pressure in nodes in all management system in pipes. And we want to be sure that we have at least 1 bar, and water level in high pressure reservoirs at least 0.3 meters. Okay, so we don't have flows in 2 different fires, but we can calculate that. So the results are that water management system status is okay, and the maximum available flow rates in those 2 fires are 20 liters in fire number 1 and 125 liters in fire number 2. And we calculated the scenario when you use 5 hydrants in fire number 2. Okay, and scenario number 4, which is a really big fire, I would say. And the general questions were, what is the maximum available water flow in selected fire locations? And we also want to know if we have enough pressure in those fires. But in this case, we designed 2 fires with selected fire flows. Fire number 1, 25 liters per second, and fire number 2, in total, we have 150 liters per second. Fire starts at 6 p.m., but the duration is actually, it's unlimited. We want to check what happens after, let's say, 2 days or 3 days of the fire extinguishing process. So the results are that after 40, or let's say until 40 hours from the start of fire, system works okay and the status is good. But what happens after 40 hours? We have some problems there. We have moderate fire flow pressures, which are under 1 bar in higher altitudes, which is not good. After 40 hours after fire start, high pressure reservoirs got empty, and the pressure drops to 0.4 bars. And pressure at fire number 2 drops to 0.8 bars. And here we have some graphs. Graph number, not number, but graphs A shows the level in the high pressure zone reservoir, and you see that after 40 hours, the reservoir gets empty. And graph B shows you the pressure in fire number 2. And on the right side of the screen, you can see hydrants, which works under very low pressures. The pressures of water is about 0.4 and even lower. Okay, so we have some conclusions and some future insights about digital models and how they could be used in fire safety. So in case of large-scale fire events, time is critical. Complete hydraulic model system are able to model critical water management aspects like fire water flow, pressure drops, ensure that critical urban infrastructure like, for example, hospitals will be unaffected by fire water insufficiency. 4 firefighting details and scenarios were tested. 2 of them were critical for existing infrastructure due to flow and pressure insurance. Well, in overall, Alytus water management network is powerful enough to cope with fires, but on the other hand, design of sustainable water management system includes many aspects, not only fire flows. Aspects like water age in pipes, power consumption, system installation costs, maintenance costs, and there's always a balance between many parameters. In case of fire, there is an option to raise the pump pressure in pumping stations. However, old pipes could break or water losses in existing pipes holes is exponent. And in summary, design and plan or development or optimization stage of water supply networks and facilities requires a comprehensive assessment and large number of conditions. And the prevention of firefighting is an important part of this task. Hydraulic model helps to find sustainable solutions and comprehensively assess the issues of pipeline diameter selection, electricity consumption, water loss, assurance, selection of various equipment, and as well as to ensure fire safety of communities and water users. So that was it from my side, and thank you very much for listening. If you have any questions, please write me or just call me. You can see contacts of me, and I would also like to say thank you for my colleagues who work together when creating hydraulic models, and also special thanks to Orunas from Indra company. He supports us with software questions very much. So thank you and enjoy next presentations.